Now that we have an understanding of how current is flowing through circuits, now that we've introduced Ohm's law, we can actually start looking at the different types of circuits and apply this knowledge to understand them both conceptually and allow us to perform some mathematical calculations. Things like finding necessary voltages, how much current is flowing, the resistance that's involved. And the first type of circuit we're going to look at is known as a series circuit. Okay? Series is just describing how the components, the battery, the wire, the light bulb, the graphic processor, the TV monitor, how they are connected. If they are in series, that simply means they are connected one after another after another. There is a single path for the electrons to travel. There's no choice. Okay, the electrons are going to go through item 1, they're going to go through item 2, they're going to go through item 3. Okay, so let's look at our picture we've seen now a few times. Okay, here's our circuit, here's the wire, the light bulb to the battery. Okay, then the process just repeats. Nothing here is optional for the electrons. The electrons must go through this wire. They must go through this wire, they must go through the light bulb. You get the idea. Everything here is wired in series. Okay? Likewise, if we go here, this is using schematic diagrams. So these are diagrams using circuit elements because no one likes drawing a battery over and over and over again. This would be a pain if you had to keep drawing this 9-volt battery picture. Likewise, I am incapable of drawing a light bulb. So if you're an electrician or if you're a physicist, if you're an electrical engineer, you use schematic diagrams. And these are examples. This is the battery. So these things are the same thing. They're showing the same circuit. This part is the battery. This is technically the cell or a cell of a battery, but it doesn't really matter in our class right now. The long wire, it's always represented by two parallel lines, one longer than the other. The longer one's the positive terminal, the shorter one's the negative. You might see the battery, it's like it's aligned a different way. You could show it like this way. Same thing, positive side, negative side. Maybe the wires are going like this. That'd be a bad circuit to draw. Anyway, so those two lines like that, those are the actual, that's the actual battery. The lines themselves, that's just the wire, pretty self-explanatory. This here is the light bulb. Light bulbs are easy to start with because we all know about light bulbs. We've all experienced, light bulbs in our daily lives. Sometimes though we won't have light bulbs. There might be different components of a circuit. One common type, especially in intro circuits, they're known as resistors. We learned about resistance before. We had a basic definition, something that impedes the flow of current. We know that it's measured in ohms, and the abbreviation for that was this, and the mathematical symbol was R for resistor. Okay. Sometimes if you're making a circuit, let's say you're making a computer, a very complex circuit, a whole bunch of circuits, and there's a certain item within the circuit that can't have much current. You gotta throttle the current down, otherwise you damage it. You might put in something whose job it is simply to resist, to lower that current. That's what a resistor is. Okay, it is a piece. It looks like this. This is actually what it looks like in real life. I'll try and show you some in the near future. It is something that is merely going to slow down the current, okay, reduce the amount of current. The schematic diagram is this, just the squiggly line. So here's the wire, squiggle, 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 wire. Light bulbs, except for maybe like LED light bulbs, many old school light bulbs, they're a type of resistor actually. That's why we see that squiggle with now a circle around it. The circle is indicating it's a resistor, but it's a resistor that's giving off light as a light bulb. Anyway, we'll use this symbol a lot. You'll see this symbol a lot as we're analyzing resistance. Okay. Now, this bullet point here is a crucial one, the perhaps most important bullet point besides just the definition, the most important thing on this slide. Because there's a single path, the current, the flow of electrons, okay, is constant. It is the same everywhere. However many coulombs of charge are passing every second at one spot, is the current at another spot. Whatever the current is here, I1, is also the current through the light bulb, I2. And I have a couple pictures. Neither of them are great representations. This is from an episode of Mythbusters. Okay, they have like a circular track and all these cars, they're driving at a steady speed. Okay, if they're driving at a steady speed and no one hit the brakes or something, the cars would all have to flow at a steady rate, the same amount of cars per second. Okay, so all these cars here, they are spaced out approximately evenly. To be honest, this picture kind of breaks down because the whole Mythbusters episode, someone slams on the brakes and they show things bunching up. But if you look right here, you see, okay, the flow of cars seems about constant. Maybe a better example is if you go to a water park, oftentimes they have things called like lazy rivers. And it's just like this giant snake of water that oftentimes is going in a loop, going in a series path, one thing after another, and you get into an inner tube and you're just floating around. Well, imagine the water in this loop. That water all must be flowing at approximately the same amount. Because if the water back here was going faster, well, you'd get like a bunch up of water here. Maybe water would start overflowing. Okay, you'd waste water. You don't want that to happen. If somehow the water slowed down here, you'd get like a gap in other places. Okay, the water is going to fill in the gaps, right? Because water is a liquid. It flows nicely and it fills things in. Don't forget, electrons have this natural repulsion. They want to have this steady, equal balance between them as best they can. So electrons kind of behave the same way as water would in one of these lazy river things. Okay, so whatever the current is in one spot, it's going to be the same everywhere else. So oftentimes, instead of labeling it as like I1 and I2, the current is just I total, the total current. It's always the same. Okay, if it's 3 volts at one spot, the total current is 3 volts. I'm sorry, 3 amps. Jeez, it must be 3 amps everywhere. Okay, well, let's now try and apply Ohm's law. Here's our example, and we'll start plugging in numbers next class and in the next assignments. I have a simple series circuit. I have a battery, I have wire, and I have 1, 2, 3. I have 3 light bulbs connected in series. I even labeled them 1, 2, and 3. They each have some amount of resistance, R1, R2, R3. Everything here is in series because if you imagine electrons flowing, electrons have to go through this wire. They have to go through this wire, have to go through this wire, have to go through this wire. They must go through each of these things. The current is the same everywhere. The current here is the current here, is the current here, is the current here. So that total current isn't changing. So we call all of that I total. I total is flowing through every little bit. There's no like path for electrons to escape. No one is injecting extra electrons. We call the voltage from the battery V total, V uppercase T. That's the only thing giving voltage. So it is the total voltage. And Ohm's law, as a reminder, looks like this. V equals IR. I can apply Ohm's law in 2 different ways. I can zoom in. I could look at light bulb 1, and I could do this. The voltage of light bulb 1 equals the current across light bulb 1 times the resistance of light bulb 1. Remember, I is always the same. It's just that I total. That's never changing. So if I gave you numbers, you could solve for how much voltage this light bulb uses up. It's based on that current and how much resistance there is. I can also zoom out and look at the total circuit. If I zoom out, I can apply Ohm's law like this. The total voltage equals the total current times the total resistance. Like that. So the total voltage would be the current going through each of the different resistors. Well, that's equal to I total times R1 plus, that should be I total right there, plus I total through R2 plus I total through R3. Okay, because there's 3 different things, each offers resistance. The current is staying the same, but the resistance doesn't have to. I'm not saying these R's have to be the same. I could do a quick little mathematical trick here. Well, I total times the quantity of R1 plus R2 plus R3 plus ... Whether the circuit has 1 resistor or 30, I could do this. Well, this means to find the total voltage, I just multiply the total current times all those resistors, simply added up. This is the total resistance. R total. This is sometimes called the equivalent resistance, sometimes REQ. Same thing. Okay? For a series circuit, and this kind of makes sense, whatever the total resistance is, it's easy. You just add up each of the individual resistors. Okay, if there's 1 resistor, the total resistance is just one of them. If there's 30 resistors, the total resistance is you add them all up. That makes sense. If you're on a road and there's 30 toll booths, each one is going to make you slow down. Okay, there are some circuits where this isn't true, so that's why I wrote it down just for series circuits. Okay, so you could use Ohm's law to look at one piece of the circuit. You could also zoom out and look at the whole thing. You just can't mix and match. You can't do apples and oranges. Either look at all the total things or look at the individual things. Okay, and again, we'll get practice with this, particularly plugging in like math problems, math numbers, next time. Thanks for watching.